Today, we're diving into an explainer about something absolutely magical that happens right in our own kitchens, even though it's actually grounded in some seriously complex microscopic science. We're going to explore the invisible architecture that builds the baked goods we all love. Because every single time you bite into a fluffy cake or a chewy piece of sourdough, you're not just eating food. You are experiencing the results of highly specific chemical, biological, and mechanical engineering.
It all really starts with one fundamental question. How does a heavy, incredibly dense lump of flour and water completely transform into a light, airy cake? I mean, it's the central magic trick of baking. Without this physical transformation, our breads would literally be bricks and our pastries would be hockey pucks. The secret to the whole shebang relies entirely on what scientists and bakers call leavening. So let's establish exactly what we're talking about here. A leavening agent is basically any substance used in a dough or batter that causes a foaming action. It introduces gas bubbles to lighten, soften, and expand the mixture. When you mix a dough, the starch in the flour and the water form a matrix. Well, actually, it's a matrix supported by proteins like gluten. The leavening agents essentially act as nucleation seeds for gas formation right inside that matrix. When heat hits it, the starch gelatinizes and sets around these expanding gas bubbles, locking that beautiful, airy structure permanently into place. To really unpack this, here's our roadmap. We'll be looking at the magic of leavening gases, biological builders, chemical leavening, the math of neutralizing value, mechanical muscle, and finally, the science of the crumb. Let's kick things off with part 1, the magic of leavening gases. The sensory properties of any baked good depend entirely on the amount of leavening gas and the rate and time that gas is formed. The 3 principal gases doing the heavy lifting are air, steam, and carbon dioxide. And once they're trapped in your batter, they undergo this wild phenomenon called Ostwald ripening. The initial air bubbles you create during mixing are absolutely crucial because they serve as the nuclei for all the other leavening gases. But here's the catch. If a small air bubble and a large one are positioned near each other in the batter, the gas will actually diffuse out of the smaller bubble and straight into the larger one. The big bubble expands and the small one just disappears. This means the initial dispersion of tiny bubbles directly dictates whether your final crumb will be coarse and open or uniform and fine. Let's talk about steam for a second, because the sheer physical power of steam is literally staggering. 1,800. That is how many times the volume of water expands when it's converted to steam during baking. As the temperature climbs in the oven, the vapor pressure of the water in your dough shoots up, powerfully expanding those existing gas bubbles. This is exactly how high-heat products, think saltine crackers, cream puffs, extruded breakfast cereals, get their tremendous rapid lift. Moving right along to part 2, biological builders, specifically bacteria and yeast. This is leavening via fermentation, where living microorganisms metabolize organic matter in the food to release carbon dioxide and create incredibly complex aromas. Take a look at the beautiful microbiology behind sourdough bread, for example. It's a true symbiosis. You've got a specific bacteria called Lactobacillus San Francisco working hand in hand with a non-baker's yeast called Saccharomyces exiguus. Together, they degrade maltose in the dough. The yeast provides the carbon dioxide for the lift, while the bacteria yield acetic and lactic acids, which is exactly what gives sourdough its famous tangy flavor profile. It's a microscopic partnership that bakers have relied on for centuries. But the crucial point here is that because yeast is a living organism, it requires absolutely perfect conditions to thrive. If you push the sugar concentration above 10%, it creates an osmotic pressure that literally destroys the yeast cells. No way around it. They need lukewarm water, too hot and they die, they love an ideal temperature range of 25 to 33 degrees Celsius, and they thrive in highly acidic environments, tolerating a pH all the way down to 2. Even spices change their behavior. Add cardamom or cinnamon, and yeast activity actually increases. But add dry mustard and it slows right down to a crawl. Which brings us to part 3, chemical leavening and those rapid reactions. Because, let's face it, sometimes a long biological fermentation just isn't practical. When we want quick breads, cakes, or cookies, we rely on the rapid reactions of chemistry. Right at the heart of this is baking soda, or sodium bicarbonate. It physically produces carbon dioxide when heated or when mixed with an acid. But the culinary stakes here are incredibly high. If you use baking soda alone without an acid, it reacts with the shortening in your batter. The result? A spotty, brown product with yellowing flavonoid pigments, an alkaline odor, and a terribly bitter, soapy flavor. Nobody wants a biscuit that tastes like dish detergent, right?
If you've ever had a bad buttermilk biscuit, it's highly likely there was more baking soda present than the acidic buttermilk could actually neutralize. To solve this exact problem, we created baking powder, which is just baking soda pre-mixed with a dry acid and a starch pillar. Now, baking powders come in two main classifications based on their reaction rates. Single-acting baking powders contain just one fast-acting acid. They react completely as soon as they hit a wet mixture at room temp. But double-acting baking powders, which are the most widely used ones today, they're a brilliant piece of chemical engineering that combine both fast and slow-acting acids. Here is exactly how that double-acting magic works in two perfectly timed phases. Step 1 is the bench operation. When you're mixing the batter, the fast-acting acid activates, releasing a portion of the carbon dioxide. This actually increases the fluidity of your cake batter so you can pour it easily. Step 2 happens in the oven. The slow-acting acid only activates when it comes in contact with heat, releasing the remaining gas to give your final baked product its ultimate volume. It perfectly times the lift exactly when the starch matrix is ready to set. It's genius.
Now for part 4, neutralizing value, or finding the perfect balance.
So how do commercial bakers know exactly how much acid to pair with their baking soda so they don't end up with those soapy biscuits we talked about? This is where the neutralizing value, or NV, comes into play. This number tells bakers exactly how many parts of a specific leavening acid are needed to completely neutralize 100 parts of baking soda. If all the soda reacts with the acid, the finished product has a perfectly neutral pH. For instance, sodium aluminum sulfate has an NV of 104, meaning it's highly efficient. Cream of tartar, on the other hand, has an NV of only 45, which means you have to use a whole lot more of it to neutralize the exact same amount of baking soda. It's a very delicate mathematical balancing act.
Beyond standard baking powder, the industry uses a few alternative chemicals for really specific jobs. Ammonium bicarbonate is fascinating because it decomposes entirely under heat. It releases carbon dioxide and ammonia gas, leaving literally zero residue. Because it leaves no residue, it doesn't mess with the pH or require leavening acid. But if your baked good has more than 5% moisture, that ammonia gas dissolves right into the water and makes the product completely inedible. Unless you want your cake to taste like window cleaner, it's strictly reserved for very dry crackers. There's also potassium bicarbonate. It lowers sodium content, sure, but it's highly hygroscopic, meaning it absorbs moisture right out of the air and leaves a bitter aftertaste, making it pretty difficult to work with. Let's pivot to part 5, mechanical leavening, or what I like to call muscle power.
Because here's the secret. None of the gases, yeasts, or chemicals we've discussed can do their jobs effectively without an initial foundation of physical air pockets. This is where your own muscle power, or let's be real, your stand mixer, comes in. When a recipe tells you to cream butter and sugar, you aren't just mixing them together. The sharp edges of the solid sugar crystals are physically cutting through the solid fat, integrating tiny little air bubbles. You are literally trapping the nucleation seeds that the baking powder is going to expand later. Whisking does something similar, but with proteins. Vigorously whipping egg whites unfolds the proteins to create a foam matrix that provides almost all the structure for delicate items like sponge cakes.
Finally, part 6, the science of the crumb.
This is where all these individual elements, the gases, the microbiology, the chemistry, and the mechanical mixing converge into the final culinary experience. Baking is truly an intricate symphony. The size, fineness, and dispersion of those invisible gas bubbles dictate what bakers call the grain of the product. The precise combination of how you mechanically creamed the butter, how carefully you controlled the yeast's environment, or how perfectly you calculated your chemical neutralizing values, all of it dictates the volume, the porosity, the softness, the color, and even the digestibility of your final baked product.
So I want to leave you with this thought. Baking is not just an art, it is a highly calibrated science happening right there in your oven. Next time you sit down and enjoy a slice of fluffy cake or a perfectly aerated piece of bread, take a moment to look at the tiny pockets of air inside it. Ask yourself, which invisible microscopic architect, was it a rapidly expanding steam bubble, a thriving yeast colony, or a perfectly timed double-acting acid that actually built this crumb? Thanks for joining me on this explainer, and keep questioning the science hiding right inside your pantry.